everyone. Today we are going to talk about time-weighted control chart, in particular QSUM and EWMA. In this lecture, we will learn about QSUM, and the next lecture will cover EWMA. In the previous lecture, we have discussed the limitation of a Schwartz control chart in that it has no memory. That is, a Schwartz control chart always use the latest update of process measurement, not utilizing the information embedded in the entire sequence of a measurement. So this makes it ineffective in detecting a small magnitude in process change. To overcome such a limitation, we will talk about two primary methods, QSUM and EWMA. QSUM method was first proposed in 1954. Let X1, X2, X3 be a sequence of observations, and Xi is assumed to follow a normal distribution with mu0 and sigma square. Here, mu0 is in control mean, mu is the current mean, and sigma indicate the standard deviation of Xi. QSUM could be constructed using either individual Xi, which means n equal to 1, or sample mean. In this lecture, we will only consider the case of n equal to 1. Let me explain the concept of QSUM. The monitoring statistic Ci at observation I is the cumulative sum of Xj minus mu0 from j equal to 1 to I. After some simple calculation, we obtain a recursive formula that Ci is the sum of Ci minus 1 plus current value of Xi minus mu0. Then we can think of three cases about effect of mean shift on Ci based on the fact that expected value of Ci equals to the sum of expected value of Ci minus 1 and expected value of Xi, which is mu I and mu0. The first case is mu I equal to mu0, which indicate no shift, and Ci will stay where it was. The second case is mu I is greater than mu0, which indicates upward shift, and Ci will drift upward. The last case is mu I is smaller than mu0, which is a downward shift, and Ci will drift downward. And therefore, we can say that the trend in Ci is an indicator of changes in the process. Let me explain the difference between the QSUM and Schwartz control chart using this example. Suppose there are 30 individual observations, then we can simply apply the QSUM formula and compute the values of Ci. Up to 20th observation, the true mean was 10, and from 21st observation, the true mean was changed to 11. We can say this example represents a small mean shift. These two figures compare how differently a Schwartz control chart and QSUM behave. As we can see, the Schwartz control chart cannot detect the mean shift occurred from 21st observation, while the QSUM successfully react to the mean shift. Now let me formulate the standard version of QSUM. This is somewhat different from the concept version of QSUM. First, upper QSUM statistic and lower QSUM statistic are defined separately. This is to decouple the negative and positive mean shift so that they are not canceling out or disturbing each other's previous effect. And the second, the standard version includes K, which is an offset value. This will make the QSUM statistic stay where it was, like the safeguard threshold. So it prevents a lot of small fluctuations from accumulating and causing QSUM chart to signal. This figure compares both upper and lower QSUM statistic with different values of K. As the figures show, as K increases, more fluctuations are disappeared. The QSUM chart can be simply implemented in two steps. First, select K and a decision interval H. Then either upper QSUM statistic or lower QSUM statistic is greater than H, then the chart gives a signal, which means that the process has changed. Then how to determine K and H? Typically, K is chosen about the halfway between mu0 and the out of control value mu1. And a common choice of H is 5 times sigma. Let's apply the QSUM chart to the same example. Recall that the target value is mu0 equal to 10 and sigma equal to 1. We suppose that the magnitude of the shift we are interested is 1 sigma. That is mu1 gonna be 11. Since K is the halfway of the shift size, so K equal to 0.5 and H equal to 5 sigma, so it is 5. We can construct the upper QSUM statistic and lower QSUM statistic and compute them for the corresponding 30 observations. In addition, we've defined n plus and n minus as the number of consecutive periods that the QSUMs Ci plus and Ci minus have been non-zero in order to estimate the new process mean. This table shows the result of the upper QSUM statistic and lower QSUM statistic and n plus and n minus. At the 8th period, n plus equal to 5, which means C plus has been non-zero for 5 consecutive periods. From the result, we can find the index where the chart gives a signal if either upper QSUM statistic or lower QSUM statistic is greater than H. Let I out denote the data point index giving a signal. Meanwhile, let I in denote the last in control data point index. And let n plus out and n minus out denote the n plus and n minus at the point of I out, respectively. Then we can estimate the process mean after the change. If Ci plus is greater than H, then the estimate process mean mu hat is mu0 plus K plus the average shift from the consecutive periods. For Ci plus is smaller than H, we can estimate mu hat in a similar way. Okay, from the table, we see the first I out equal to 29 in the Ci plus chart because each value 5.28 is greater than 5. And the corresponding n plus out equal to 7, which yields I in index is 22. Then we can estimate the new process mean by 10 plus 0.5 plus 5.28 divided by 7, which equals to 11.25. Okay, compared to the true mean, 11, the estimated value is quite accurate. In the QSUM chart, K and H play an important role. Note that in some textbook, K and H are expressed by the lower capital K and H with sigma. Regarding determination of K and H, I introduced a simple approach in the previous slide. More general QSUM chart design is based on proper choice of average run length, ARL. We should select appropriate K and H so that we have a large enough ARL0 when there is no process change and small enough ARL1 when there is a process change. However, the impact of K and H on ARL is complicated. I'm going to introduce two approaches. One is to use result from literature, and the other one is use simulation. Okay, some results are available in literature. The left table is ARL performance of the QSUM with K equal to 0.5 and H equal to 4. For example, the 1 sigma mean shift can be detected in 8.38 samples on average with K equal to 0.5 and H equal to 4. Recall that for the same mean shift, the Schwartz control chart would require 43.96 samples on average. The right table shows the value of K and the corresponding H that gives ARL 0 to be 370. As you see, as K increases, the corresponding H decreases. Instead of using observations directly, we can standardize the value of observations. We can standardize them by subtracting mu0 from xi and then dividing by sigma. There are two advantages to standardizing the QSUM. First, many QSUM charts can have the same values of K and H, and the choice of these parameters become not scale dependent. Second, a standardized QSUM leads naturally to a QSUM for controlling variability. Before we move on EWMA, I have several comments to discuss. So far, we consider individual observation for the QSUM chart, that is n equal to 1. The QSUM chart can be applied to a sample mean by replacing xi and sigma by the corresponding sample statistics. If we are only interested in process changes in one specific direction, and then we can easily use one-sided QSUM by simply selecting either C+ or C-. QSUM is good at detecting process changes of small to moderate magnitude, while the Schwartz control chart is good at detecting process changes of large magnitude. In practice, one can combine both methods for purpose of effective detection. Okay, in the next lecture, I will talk about another time-weighted control chart, EWMA. Thank you.